So number 13 reads that we have a sinusoidal electromagnetic wave with a frequency of 6.10 10 to the 14 hertz. So an EM wave. And they said that our frequency was 6.10 times 10 to the 14 hertz. Okay. It travels in a vacuum in the positive X direction. So this is, in a vacuum. Positive X direction. And then it says that the magnetic field is parallel to the y-axis and has an amplitude of 5.80 10 to the minus 4 Teslas. And so then we have our amplitude of the magnetic field. And I like that not notation, but you could do P's for peaks or M's or maxes or whatever's. Whichever one makes you happy, but I like the knots. 5.80. 10 to the negative 4th Teslas. And it says that this was in the, we'll put it in the positive Y direction. Okay. And then it asks, find the magnitude and direction of the electric field, and then write down the wave function for the electric and magnetic fields in the form of our, equations that we worked on, refiguring out. So what we want to figure out the electric field. And so we can do the magnitude and the direction. So let's start off with our magnitude. So the magnitude of the electric field is C times the magnitude of the magnetic field. That was that implication that we got by having the energy densities being equal. Then we got that the E was C times B, no matter which kind it is, as long as they're all the same. Peak, peak, RMS, RMS, same position, time kind of things. Okay. And so we know the B, we know C. So this will be our 3 times 10 to the 8th. And then this is our 5.80 times 10 to the negative 4th. And so we get how much? Thank you. 174,000. So 1.74. 1, 2, 3, 4, 5. 10 to the 5. And we'll go with the volts per meter. But we could still do newtons per coulomb if you wanted to. It's all good. And then let's go in and figure out which way it's going to point. Okay. So because the wave's going to travel, I'm going to call this the plus X direction. So it was traveling in the X direction. Then I'll do that this is the plus Y type of things. So the direction of travel was that pointing vector or the velocity vector. So I'm going to go with the big, capital S vector for the pointing vector. And then we have the magnetic field was in the positive Y direction. So we'll put in RB. Goes like this. And so then we got to figure out which way the E goes. Okay. And I also got to figure out which way my coordinate system goes, right? So we're going to go in, we're going to remember our right hand rule, number 1. So that's the, the fingers, the palm and the thumb. Okay. And so to begin with, we do the coordinate system is alphabetical. So this is, plus X, this is plus Y, plus Z. So we're going to put our, page rotates, fingers in the X, rotate my hand until the Y points out of the palm, thumb points in the positive Z direction. So X, Y, Z. So this out of the page slanty one, this is the plus the Z direction, like so. Okay. And now we need to go in and figure out which way the electric field goes. And the way that that went was way back here when I drew my picture. There they are. E's were the fingers, out of the palm was the B, and then the thumb was the, the pointing vector or the velocity. Okay. So E is the fingers. The B, as usual, points out of the palm. And then our direction of propagation, or the direction that the energy transports, is in the thumb direction. But now what's funny is we have the out of the palm and the thumb, and we got to figure out which way the E's go, which way the fingers go, right? So I've got that my, number one, my right hand, my thumb goes like this, right? I'm going to rotate it until the B's point out of my palm. Make sure that y'all can see. All right, so thumb is this way. That's the S. B is up, so it's out of the palm. Fingers are going into the page. So then my electric field heads back like this. And my B's in the way. Terrible. There we go. All right, let me move the B. Red choices here. There we go. So the electric field is in the negative Z direction. Okay. So then I can write down that my electric field vector at this position in time is going to be our 1.74 times 10 to the fifth, volts per meter or newtons per coulomb. And then it's going to be, in the negative Z direction. There's our answer for the electric field for part A. Okay. How'd we do? Okay, hold on. Confused by the plus X plus Y, they're not the same as the vectors. No, that's the coordinate system, right? So we have an XYZ coordinate system. And so without drawing anything, I can figure out the coordinate system. It's the fingers, the out of the palm, and the thumb for the XYZ. Okay. So I don't care about any of these. If I made my X go to the right, and that's because I kept, not necessarily. But what we do know is we know that the wave is traveling in the X direction, in the positive X direction. So that's the S, or the velocity vector, goes this way, which is the thumb, right? And we know that the B was in the positive Y direction, which is we made up on the page. Now I made the X go to the right because I kept drawing all my waves this way, right? If we look at the pictures, the waves travel, to the right on my page. And so I made that the plus X direction. And it's for the way they usually write out the waves, that's almost always how they draw them. I mean, they can go other ways, but that's not how we usually draw it. So this was going to be the X is the horizontal for our waves. And then what we had was that the B's were in the Y direction, the plus Y. And I just need to figure out which way E went. Okay. And let's go backwards now. So if we know that the E is into the page, right? And then I rotate my hand so that the B points out of the palm. So E is into the page, B is out of the palm, up on the page. Thumb points to the right on the page. That's the direction at which it travels. Better? Yeah, so I needed a coordinate system. And then we could tell which way the things went based on what they said, in the plus X and the plus Y. And then I could figure out the missing one. So this was a funny one because it was the backwards one, right? They gave me the S and the B and which way was the E kind of stuff. So, all right. So 13, that was part A. And then part B, write down the functions for the electric and magnetic fields in that form. And so the form that we found for our electric and magnetic fields was that my E as a function of position and time was the peak value times our sine of omega t plus or minus kx. And then the B looked the same thing. Okay. And so now we have F, but I want omega. I have B naught and E naught, so we've got those, but I'm going to need Ks and omegas. Okay, so let's work to get those, and then we can write down our equations. Okay, so since F is the 6, then we find that our omega is 2 pi times the frequency. Okay, because I did that. Oh, that one's right here. Omega is the 2 pi times the frequency. And we got our frequency. That's the 6.10 times 10 to the 14 hertz. And so this will be our omega, and again, it'll be in the like the radians per second kind of thing. Get it? This is 6-ish times 6 would be like 36. So 3.6 or maybe 3.7, 10 to the 15. There it is, 3.83. That was off a bit. There we go. Got that one. Now I want to use, we have options to get the K. We know that K is our, just like this, right? That K is 2 pi on lambda, okay? And we know that the wave speed, which is C, because it said it was in a vacuum, is our, lambda F. And we got the F, we know C, we could get lambda, put the lambda here and get K. But I want to use the other formula. So I showed you that B was lambda over T, and that we could rearrange this to get omega over K. So I want to practice with that one because we haven't used it. Okay. So I'm going to start with the V is omega over K, and we're going to solve for K. Okay. So what we end up with is that our K is omega divided by C. And we just found the omega. So the 3.83 10 to the 15th over our 3 10 to the 8. Okay. 15 minus 8 is what? 7. So 10 to the 7. This goes in once. This goes in twice. And almost 8. So 1.28 10 to the 7. I'm going to guess the 8. I'm probably going to regret that. K is in the radians per meter. Oh, wow. Cool. All right, there we go. So we got those ones. So now we can, write the formula. And this is really what we're going to do with these wave formulas is it's just like what you guys saw in 12. It wasn't like we're going to plug in a time, plug in an X and calculate stuff, nor are we going to be given things and try to solve for the time or the X. We're just really going to just, plug into the equation or pull out of the equation and identify things. So it's going to be easier than, you might fear. So let's do the electric field one. So then my electric field at some X and T is going to be the amplitude. And so we'll put in, this is the 1.74 times 10 to the 5th volts per meter times our sine of omega, which is this number, 3.83 times 10 to the 15 radians per second times the time. Now, is it going to be the -1 or the +1, and why? How do we know? This goes back to my transformations upon a known function that I should have colored better. And I flubbed up when I first wrote. So what do we think? Okay, that's fine. Fair answer. Okay, then let's go back. So here, this was the f of x is x squared, so this parabola. And so the thing is, if we take this graph and shift it 2 units to the right, then the way we write it is x minus 2. Because again, if you plug that when x is 2, you get 2 minus 2, which is 0. 0 squared is the 0. That's the vertex. Okay. So when you subtract, it goes in the positive x direction. And when we add, it goes in the negative x direction. Okay. So are we good with that? Do y'all recall this from like algebra class? I mean, it might have been a long time. Might do it in pre-cal some, but I think really it's college algebra is where it is. That's all right. That's why we kind of remind things, Well, at least that's what I try to. Great. So what happens is that between the t term and the x term, if it's subtracting, then that's going to the right in the positive x direction. And if it's the plus, then it goes to the left, which is in the negative x direction. I should have switched my colors. I didn't recognize I had them backwards until I was relooking at it. And so notice that in the problem, they told us that our electromagnetic wave had this frequency. It was traveling in a vacuum towards the plus x direction. So if we're going to do the positive x direction, then what sign do we have in between the terms? So we're going to go to the right. Yeah, then we're going to do the minus. Are we good? Mm-hmm. So it'll be the minus sign. So we pick up the minus. They got to write down the k. This one here, the 1.28, 10 to the 7 times our x. And there it is. So these are the things we do with those formulas. We just kind of, in this case, we were loading it. And in other cases, we'll pull information out of it. Given like this, we would go, oh, this is the amplitude. This is the omega. This is the k. We could find from the omega, we could get the period or the frequency. From the k, we could get the wavelength, and find things. Yeah, ain't it? And then let's go in, like I said, it's interesting. In some sense, it's kind of interesting how many of those things you learned before are actually important to us now. Because I'm pretty sure at the time you might have struggled to go, why is this important to me? But a lot of them do get used. Let's write down the B one. So I'm going to change my color to purple. That's how I usually color the magnetic field. The B amplitude, they told us this 5.80, 10 to the negative 4 Tesla. The same sine function, and it's exactly the same. So, I'll write it, but I usually don't like writing it because it's, identically the same. There we go. There's the B. Questions? And so then this ends our examples.